Hi everyone, welcome back to the channel. In today's video, we're going to explore one of the most common exceptions to the octet rule, the incomplete octet. We'll focus on boron trifluoride, BF₃, and step by step, we'll draw its Lewis structure together. You'll see why boron ends up with only 6 electrons, why this is perfectly stable, and how this exception fits into what we know about chemical bonding. Before exploring the exceptions to the octet rule, we need to remember what the octet rule actually tells us. For most main group elements, stability is achieved when an atom is surrounded by 8 electrons in its valence shell. Many molecules follow this rule very well. However, some do not, and boron trifluoride, BF₃, is one of the most common examples. Now we're going to draw the Lewis structure of BF₃. If you haven't seen our earlier video on drawing Lewis structures, you might want to check it out. It explains the step-by-step method for any molecule. Here, we'll follow the same approach. Just like in the previous video, the first task is to figure out the total number of valence electrons in the molecule. Boron is in group 13 of the periodic table, which means it contributes 3 valence electrons. Each fluorine atom is in group 17, providing 7 valence electrons. Since BF₃ contains 3 fluorine atoms, that's 3 times 7, giving 21 electrons from fluorine. Adding boron's 3 electrons brings the total to 24 valence electrons. This is the exact number of electrons that must be represented in the Lewis structure. Next, we determine the central atom. The least electronegative element, excluding hydrogen, goes in the center. In BF₃, boron is less electronegative than fluorine, so it sits in the center with the 3 fluorine atoms surrounding it. We now draw a single bond from boron to each fluorine. Each bond represents 2 shared electrons, so the 3 bonds use up 6 of the 24 electrons. That leaves us with 18 electrons to distribute as lone pairs. The next step is to complete the octets of the terminal atoms, which are the 3 fluorines. Each fluorine already shares 2 electrons in its bond with boron, so we need to place 6 more electrons as 3 lone pairs around each fluorine. Placing 6 electrons on each fluorine uses all 18 remaining electrons. Now, each fluorine atom has a complete octet, 8 electrons total. Now let's focus on boron, the central atom. It forms 3 single bonds with fluorine, giving it 6 electrons. That's less than an octet, unlike the fluorines, which each have 8. At first, this might seem unusual, but it actually sets us up to understand why BF₃ is stable despite having an incomplete octet. Think of the octet rule as a goal. 8 electrons is what atoms usually aim for, but not every atom has the resources to reach it. Boron starts with only 3 valence electrons. When it bonds with 3 fluorine atoms, it shares those 3 electrons and gets 3 more in return. Do the math. 3 plus 3 equals 6. So why doesn't boron just take more electrons to complete its octet? It ran out of seed electrons. Boron used everything it had to make the 3 bonds. And fluorine won't share. Fluorine is the greediest element because of its high electronegativity. It holds tightly onto its extra electrons and refuses to form a double bond to help boron reach 8. Because of this, boron is perfectly stable with just 6 electrons. This situation is called an incomplete octet, and it's the most common exception you'll see in group 13. That's it for today's lesson on boron trifluoride and the incomplete octet. Thanks so much for staying until the end. If you have any questions or want to share your thoughts, feel free to drop them in the comments below. I'd be happy to help. See you in the next video.